You think you understand time. You've experienced decades. You've read about centuries. You've learned about millennia, the rise and fall of civilizations, the migration of peoples, the construction of monuments that have endured for thousands of years. You know what ancient means. But you're holding a rock right now, and this rock is 4 billion years old. 4 billion. Not million. Not thousand. Billion. With a B. Before this rock formed, there were no continents. No oxygen in the atmosphere. No animals. No plants. No fungi. The sun was dimmer. The day was shorter, 5 hours instead of 24. The moon loomed 3 times larger in the sky. This rock has been here since the beginning. And it remembers everything. You're standing in the Canadian Shield, in a remote region of northwest Canada near the shores of the Great Slave Lake. The landscape here is ancient in a way that transcends description. Low, rounded hills of exposed bedrock stretch to the horizon. No soil covers them. No vegetation, except for patches of lichen clinging to crevices. Just bare rock, polished by 4 ice ages, scoured by glaciers that have come and gone like seasonal tides. The rock beneath your feet is Acasta Gneiss. Pronounced Gneiss. It's streaked with bands of gray and pink, layers that have been folded, compressed, and metamorphosed over eons. The surface is rough under your hand, crystalline, sparkling faintly in the sunlight. You can feel the texture of individual mineral grains, quartz, feldspar, biotite. This rock is 4.03 billion years old. It formed when Earth was only 500 million years old, when the planet was still cooling from its violent birth, when the late heavy bombardment was pelting the surface with asteroids and comets. To put this in perspective, the time between the formation of this rock and the appearance of the first dinosaurs is greater than the time between the dinosaurs and you. The oldest fossils are 3.5 billion years old. This rock predates them by 500 million years. It formed in an Earth so alien that nothing alive today would recognize it. Scientists study these ancient rocks because they're witnesses. Time capsules. The only physical record of a chapter in Earth's history that is otherwise lost. Continental plates have subducted, recycling nearly all of Earth's early crust back into the mantle. Erosion has worn down mountains. Metamorphism has transformed rocks beyond recognition. Less than 1% of the planet's original surface remains. But this rock survived. And locked inside its crystalline structure are secrets about early Earth that exist nowhere else. The question is, how do you read a rock? You kneel and examine the rock more closely. Its banded structure reveals a violent history. These bands are layers that were once horizontal, deposited as sediment or crystallized from molten magma. But they've been twisted, folded, compressed by forces so immense they bent solid rock like clay. This is what metamorphism does. Heat and pressure transform rocks, recrystallizing their minerals, reorganizing their structure. The Acasta Gneiss has been metamorphosed multiple times, each event leaving its signature in the mineral composition, the crystal orientation, the chemical ratios. Geologists can read these signatures. They measure isotope ratios, the relative abundance of different atomic variants of the same element. Certain isotopes decay at known, constant rates, providing natural clocks. Uranium-238 decays into lead-206 with a half-life of 4.5 billion years. By measuring how much uranium has decayed in a mineral, scientists can calculate when that mineral crystallized. But here's the challenge: metamorphism can reset these clocks. Heat causes atoms to migrate, disrupting the isotope record. Some minerals are more resistant than others. And some preserve multiple ages, layers of time stacked within a single crystal. The most resilient mineral is zircon. Zirconium silicate. Tiny crystals, often smaller than a grain of sand, but nearly indestructible. Zircons resist weathering, resist melting, resist metamorphism. They incorporate uranium into their crystal lattice when they form, but reject lead. This means any lead found inside a zircon must have come from uranium decay. It's a closed system, an uncontaminated clock. Inside the Acasta Gneiss, scientists have found zircon crystals that are even older than the rock itself. Some date to 4.2 billion years. These crystals formed in earlier rocks that were melted, mixed, and recrystallized into the gneiss. But the zircons survived. Their inheritance, fragments of a previous world, incorporated into a new one. And when scientists analyze the oxygen isotopes in these ancient zircons, they discover something impossible. The isotope ratio suggests that when these crystals formed, liquid water was present. Oceans. On a planet that was supposed to be a molten hellscape, where surface temperatures exceeded 1000 degrees Celsius. Yet the chemistry doesn't lie. The zircons show evidence of water-rock interaction, of hydrothermal alteration, of sedimentary processes that require liquid water. This means oceans formed earlier than anyone thought possible. Maybe within 200 million years of Earth's formation. Maybe even sooner. The planet cooled faster than our models predicted. Water condensed from volcanic outgassing. The surface solidified, even as the interior remained molten. But we don't understand why. Why did Earth cool so quickly when similar planets, Venus, Mars, did not? What conditions allowed oceans to persist despite continued asteroid bombardment? How did early continents form in such a water-dominated world? We don't know. You travel now, moving forward through time rather than back. From Canada to Australia, to the Pilbara region of Western Australia. Here, the landscape is red and ochre, stained with iron oxides. The rocks are younger than the Acasta Gneiss, only 3.5 billion years old. Still ancient beyond comprehension, but from an Earth that had begun to change. You're standing in front of a stromatolite fossil. It looks like a layered dome, about the size of a basketball, with concentric bands like tree rings. The rock is hard, silicified, turned to stone by billions of years of mineralization. But once, this structure was alive. Stromatolites are built by cyanobacteria, photosynthetic microorganisms that form mats on seafloors. The bacteria secrete sticky substances that trap sediment. Layer by layer, over years and decades, they build these dome structures. Living stromatolites still exist today, in places like Shark Bay in Western Australia, growing in shallow, salty water where few predators can survive. But 3.5 billion years ago, there were no predators. No grazers. No animals at all. Stromatolites dominated shallow marine environments, forming vast reefs that stretched for kilometers. They were Earth's first large-scale ecosystems. The first visible life. And they were doing something revolutionary, producing oxygen. Cyanobacteria photosynthesize. They split water molecules, use the hydrogen to build organic compounds, and release oxygen as waste. For hundreds of millions of years, this oxygen didn't accumulate in the atmosphere. It was absorbed immediately by dissolved iron in the oceans, precipitating out as iron oxide, rust. The banded iron formations you see in Pilbara, layers of red and black rock alternating like pages in a book, are the result of this process. Each band represents a cycle of oxygen production and absorption. But eventually, around 2.4 billion years ago, something changed. The oceans became saturated with oxygen. There was no more dissolved iron to absorb it. And the oxygen began to accumulate in the atmosphere. This event is called the Great Oxidation Event. It was Earth's first planetary-scale environmental catastrophe, and its first transformation toward habitability for complex life. For the anaerobic organisms that dominated Earth, oxygen was toxic. A poison. It damaged cellular machinery, destroyed proteins, killed on contact. The Great Oxidation Event triggered a mass extinction. Entire lineages of bacteria vanished. The world that had existed for billions of years was irrevocably changed. But for the survivors, for organisms that evolved to tolerate oxygen, to use it, to harness its chemical energy, this catastrophe became an opportunity. Aerobic respiration is far more efficient than anaerobic metabolism. It produces 15 times more energy from the same amount of glucose. This surplus energy enabled complexity. It made multicellular life possible. It paved the way for everything that came after: plants, animals, fungi, you. The stromatolites triggered a revolution they couldn't control. They transformed the planet's chemistry, its atmosphere, its evolutionary trajectory. All by accident. All as a byproduct of their metabolism. And we can see the evidence in the rocks. In the iron formations. In the shift in sulfur isotopes. In the appearance of red beds, terrestrial sediment stained with iron oxides, indicating that oxygen had spread from the oceans to the atmosphere to the land. But here's what we don't understand: why did the Great Oxidation Event happen when it did? Cyanobacteria evolved hundreds of millions of years earlier. They were producing oxygen for 500 million years before it accumulated. What changed? Was it tectonic activity slowing down, reducing volcanic gases that consumed oxygen? Was it a tipping point in ocean chemistry? Or something else entirely? We don't know. You're in a laboratory now, far from the outcrops. A sample of ancient rock sits under a microscope, this one from Greenland, dated to 3.7 billion years old. The rock is slate gray, fine-grained, metamorphosed. To the naked eye, it looks unremarkable. But under magnification, structures emerge. Tiny filaments. Branching shapes. Patterns that look organic. They're made of graphite, pure carbon. And their carbon isotope ratios suggest they were once alive. This is among the oldest evidence of life on Earth. Not fossils in the traditional sense, no preserved cells, no identifiable species. Just chemical signatures. Carbon that was once cycled through living metabolism, leaving an isotopic fingerprint that persists billions of years later. But not everyone agrees this is life. The structures could be abiotic, formed by non-living chemical processes that mimic biological patterns. The carbon isotopes could be explained by geological processes. The debate continues. Every claim of ancient life is scrutinized, questioned, challenged. As it should be. Because the implications are profound. If life existed 3.7 billion years ago, just 800 million years after Earth formed, then life arose quickly. Almost immediately, in geological terms. This suggests that abiogenesis, the origin of life from non-living chemistry, might be relatively easy. Common. Inevitable on any planet with the right conditions. And if life arose quickly on Earth, despite the asteroids, despite the lack of oxygen, despite conditions we'd consider hostile, then it might have arisen quickly elsewhere. On Mars, before its atmosphere was lost. On Europa, in oceans beneath ice. On countless exoplanets orbiting distant stars. But the opposite could also be true. If we're misinterpreting these ancient rocks, if these structures are not biological, then the origin of life might be rare. Life might have taken longer to appear than we think. The requirements might be more stringent. And we won't know until we find more rocks. Older rocks. Better preserved rocks. Or until we find life elsewhere. You're holding a different rock now, from a different era. This one is 66 million years old, young by geological standards, but significant. It's a layer of clay, gray and fine-grained, sandwiched between other sedimentary rocks. It's only a few centimeters thick, easy to miss. But this layer marks a boundary. Below it, fossils of dinosaurs, ammonites, and countless other species are abundant. Above it, they vanish. Gone. 75% of all species on Earth disappeared at this boundary. This is the KPG boundary, the line between the Cretaceous and Paleogene periods. The line drawn by an asteroid. And if you analyze this clay layer, you find something that doesn't belong: iridium. An element rare on Earth's surface but common in asteroids. The layer is enriched in iridium by a factor of 30, sometimes 60. A spike so dramatic, so global, that it can only come from one source: an extraterrestrial impact. The asteroid struck the Yucatan Peninsula, creating the Chicxulub crater. The impact released energy equivalent to 10 billion Hiroshima bombs. It vaporized the asteroid, the bedrock, and everything within hundreds of kilometers. It ejected trillions of tons of rock and dust into the atmosphere, which spread globally, blocking out the sun for months or years. The darkness killed plants. The collapse of photosynthesis starved herbivores. The herbivores' extinction starved carnivores. The food chain collapsed from the bottom up. The dinosaurs, which had dominated terrestrial ecosystems for 160 million years, were gone within a geological instant. But some organisms survived. Small mammals. Birds, the descendants of dinosaurs. Crocodiles. Turtles. Some plants. Organisms that could burrow, hibernate, scavenge, or tolerate disruption. And in the aftermath, over millions of years, these survivors radiated into new forms. Filled the empty niches. Mammals, which had been small and nocturnal under dinosaur dominance, diversified into thousands of new species. Primates evolved. Eventually, humans. The asteroid didn't just kill. It reset the system. It created opportunity. It allowed evolution to explore pathways that had been foreclosed by existing ecosystems. The rocks preserve this story. Not just in the iridium layer, but in the fossil record. In the carbon isotope shifts that indicate ecosystem collapse. In the shocked quartz crystals shattered by pressures only possible in impacts or nuclear explosions. In the tektites, glassy droplets of melted rock ejected from the crater and scattered across continents. Yet despite all we know about this extinction, there are questions we still can't answer. Why did some lineages survive while others perished? Size isn't the only factor. Some small dinosaurs went extinct while larger crocodiles survived. Diet isn't the only factor. Some herbivores survived while others didn't. Was it luck? Was it specific adaptations we don't recognize? Or was the pattern more random than we assume? We don't know. And the KPG extinction is just one of 5 major mass extinctions in Earth's history. Each one preserved in rocks. Each one resetting the trajectory of life. Each one raising questions we're still trying to answer. You're back in Canada now, at a different outcrop. But this time, you're not looking at the surface. You're examining a drill core, a cylinder of rock extracted from 3 kilometers below the surface. This rock has never seen daylight. It's been buried, compressed, heated, transformed. But it survived. Deep rocks tell a different story than surface rocks. They reveal Earth's internal processes. The movement of tectonic plates. The formation and breakup of supercontinents. The cycling of elements between surface and interior. Earth is not static. The continents drift. They collide, forming mountain ranges like the Himalayas. They split apart, forming ocean basins like the Atlantic. This dance has repeated throughout Earth's history. Continents coalesce into supercontinents, then fragment again. Pangaea. Rodinia. Columbia. Each lasting a few 100 million years before breaking apart. And each cycle leaves its signature in the rocks. In the orientation of magnetic minerals, which record ancient magnetic field directions. In the pressure-temperature conditions recorded by metamorphic minerals. in the isotope ratios that reveal where rocks formed and how they moved. By reading these signatures, geologists have reconstructed Earth's tectonic history back 2 billion years, sometimes further. They've mapped continents that existed when life was still microscopic. They've tracked ocean basins that opened and closed before animals evolved. But the deeper we go into Earth's history, the less certain the reconstructions become. The rocks are more metamorphosed. The evidence is more fragmentary. The interpretations are more contested. We know there were continents 4 billion years ago, the zircons prove it. But how large were they? Were they scattered island arcs, or substantial land masses? Did plate tectonics operate the same way then as now, or was Earth's heat budget higher, driving different geodynamics? We don't know. And these aren't just academic questions. Understanding Earth's early tectonic evolution is crucial to understanding how life emerged and evolved. Continental crust provides nutrients to oceans. Tectonic activity drives volcanic outgassing, replenishing the atmosphere. Subduction zones recycle surface materials, maintaining chemical balance. Without plate tectonics, Earth might resemble Venus, a dead, stagnant world with a crushing atmosphere. Plate tectonics might be what makes Earth habitable. And if that's true, then habitable planets might be rarer than we think. You're standing at the outcrop again, hand resting on 4 billion-year-old stone. The sun is setting. Long shadows stretch across the ancient bedrock. The same rock that's been here since the planet's infancy, that's witnessed every extinction and every recovery, that's recorded the rise of oxygen and the birth of continents. And you realize, this rock knows the future. Not in a mystical sense. But because the patterns preserved here, the cycles of climate, the rhythms of tectonics, the trajectories of evolution, they reveal the constraints, the possibilities, the deep rules that govern how planets work. Earth has been warmer than today. Much warmer. The rocks show periods when there were no ice caps, when forests grew in Antarctica, when sea levels were hundreds of meters higher. And Earth has been colder, snowball Earth events when glaciers covered the planet from pole to equator, when only equatorial oceans remained liquid. Life survived both extremes. But barely. Each extreme brought extinctions. Each recovery took millions of years. We're living in an interglacial period, a warm spell between ice ages. Our entire civilization has existed in this narrow window of climatic stability. 10,000 years. A blink, in geological time. And we're changing the climate faster than it's changed in millions of years. Pumping carbon dioxide into the atmosphere at rates that rival major volcanic events. Warming the planet at a pace that exceeds anything in the recent geological record. The rocks can't tell us exactly what will happen. Earth's climate is complex, with feedbacks and thresholds we don't fully understand. But they can tell us what's possible. What's happened before. What the planet is capable of. And they tell us this: Earth will persist. Life will persist. But individual species, individual ecosystems, those are fragile. When conditions change too quickly, extinctions follow. The rocks are full of extinctions. We're writing our own chapter in Earth's geological history. A layer that future geologists might call the Anthropocene, the age of humans. A layer marked by plastics, concrete, radioactive isotopes, and a spike in atmospheric carbon dioxide. A boundary in the rock record, like the KPG boundary, signifying a moment of planetary transformation. But unlike the asteroid, we can see it coming. We can read the warnings written in ancient rocks. We can choose what kind of boundary we create. The stars are visible now. The same stars that shone on this rock when it formed, though many of those stars have since died, their atoms scattered and reformed into new stars, new planets, new worlds. 4 billion years is long enough for stars to be born and die. Long enough for galaxies to collide. Long enough for life to emerge from chemistry and evolve into consciousness. And this rock has been here through all of it. But here's the truth we forget: this rock doesn't remember. It doesn't think. It doesn't know its own history. It's just atoms, arranged in patterns, preserving information. We're the ones who remember. We're the ones who read the rocks, who decipher their secrets, who connect the fragments into narratives. We're the ones who look at ancient zircons and see oceans. Who look at stromatolites and see the beginning of oxygen. Who look at iridium layers and see catastrophe. The rocks are archives. But archives are meaningless without readers. And despite everything we've learned, despite isotope dating and electron microscopes and global databases of geological data, we've barely started reading. There are ancient rocks we haven't sampled. Drill cores we haven't analyzed. Isotope systems we haven't explored. How did life begin? We don't know. We have hypotheses, but no rocks old enough to preserve direct evidence. What triggered the Great Oxidation event exactly when it happened? We don't know. Why did Earth maintain its magnetic field when Venus and Mars lost theirs? We don't know. How many mass extinctions occurred in the first 3 billion years of Earth's history, before animals evolved to leave obvious fossils? We don't know. Every answer in geology raises 3 new questions. Every technique we develop reveals complexity we hadn't imagined. The deeper we look, the more we realize how much is still hidden. But that's not failure. That's the point. The rocks are patient. They've been here for 4 billion years. They can wait for us to develop better instruments, better theories, better questions. They're not going anywhere. And neither should our curiosity. Because the greatest secret hidden in Earth's oldest rocks is not what they tell us about the past. It's what they reveal about how much we still have to discover.